Okay. Good evening, everyone. We are Group 13, and today we are excited to share our insights on a revolutionary building material that is shaping the future of sustainable construction. Our presentation focuses on autoclaved aerated concrete, or AAC, which we will explore under the theme An Innovative Building Material. Providing you with an overview of AAC. AAC stands for Autoclaved Aerated Concrete. It is a type of precast concrete material which was pioneered in the 1920s by Johan Axel Eriksson in Sweden. It is distinguished by its uniform distribution of air bubbles, providing insulation. Now, coming to its properties. AAC boasts several advantageous properties. These include lightweightness for easy handling and transport, superb insulation for temperature regulation, fire resistance without emitting harmful gases, sound insulation to reduce noise transmission, and durability against pests, rot, and mold. Now, moving to its manufacturing process. The manufacturing process of AAC basically involves transforming the basic materials into sustainable or eco-friendly building blocks. First comes the raw material preparation and mixing, wherein ingredients such as silica, sand, cement, lime, and water are blended together. Aluminium powder as an ingredient is used, which initiates a chemical reaction, which is then followed by the reaction generating expansion, which results in a porous, lightweight texture. Then comes casting, pre-curing, and cutting. Casting basically involves the aerated slurry being poured into molds to solidify. Once set, the material is removed from the folds and cut into specific sizes and shapes, which is basically the demolding process, which is then followed by the customization process, which allows for the tailoring of autoclaved aerated concrete blocks to meet construction specifications. And finally comes autoclaving, wherein the cut blocks or panels undergo curing in autoclaves under high pressure steam. This process enhances strength, durability, and insulation properties of the concrete. It ensures both structural integrity and a lightweight nature of the final product. As you can see from the diagram, the manufacturing process of AAC is very well explained. First comes the mixing process where the raw materials are blended together, followed by molding and pre-curing wherein the aerated slurry is first poured into molds to solidify, and once set, it is then removed from the molds. Then comes the cutting process where it is cut into specific sizes and shapes. Then it undergoes curing under high pressure steam, that is the autoclave curing, which enhances its strength and durability. And then it is finally stored. Similarly, we have a diagrammatic explanation of the production of reinforcing mesh, where the first step is the anti-rust treatment, followed by mixing, pouring, pre-curing, cutting, autoclave curing, and finally it is packed and transported. With a good understanding of how AAC is made and a brief overview of its application, I shall now hand over to Ishani Jha to discuss the properties of AAC, its advantages and disadvantages. Over to you, Ishani.
Thanks, Khushi. Now, moving concrete, we'll explore more about the properties of AAC. AAC has the following properties that make it a lucrative option amongst modern day construction. It is lightweight. The weight of AAC is one-fifth the weight of traditional concrete. It provides thermal insulation. Its porous structure offers superior insulation. It it has several R's of fire resistant and gives resistance to fire exposure. It has acoustic insulation and reduces sound transmission. It is eco-friendly and promotes sustainable construction. It is pest resistant and is resistant to mold and pests due to its inorganic materials. High workability and easy flexibility. It is easy to cut, drill, and shape and reduces labor costs. AAC has high durability and can withstand harsh weather and chemicals, and it has comparatively lower maintenance. Also, it provides dimensional accuracy and ensures tight joints and smooth finishes. Now, moving forward with our discussion, there's a question that hovers in our minds: that what are the features that makes AAC stands out if we look out for sustainable building materials? AAC has the following features that make it lucrative amongst its modern day counterparts. It has high environmental sustainability, that is, it is more energy efficient than traditional concrete. It reduces carbon dioxide emissions and landfill waste. It is highly energy efficient and provides superior thermal insulation and lower energy use and costs. AAC provides resource efficiency and reduces the transportation costs and construction waste. It is safe and durable. It enhances fire safety and promotes minimal maintenance. Also, it is a better option if we look out for healthier living. It improves indoor air quality by resisting pests and mold. It is versatile and is suitable for various styles and construction needs. Also, if we look out for the future options, it is compiled with tightening energy and environmental regulations. Now, moving forward with the disadvantages of AAC, they are higher production cost. It is expensive due to specialized processes. Also, as it handles issue that can complicate finishing, it has manufacturing sensitivity. It has higher water absorption, which reduces the breathable finishes to avoid weathering. Also, it promotes efflorescence damage and can cause efflorescence and structural cracking. When wet, it can cause strength loss as the joints may weaken and disintegrate with moisture. It also has environmental vulnerability, which makes it susceptible to degradation in harsh conditions. Now, to dive further into the topic and explain various the other vital features and insightful experimental data, I'll hand over it to Rohit.
Thanks, Isani. Now we'll be moving on to the research part. The research on AAC not only helps in improving its existing properties, but also opens new avenues for sustainable practices. Now I will take you through the carbonation of AAC and how recycled materials can complement the traditional AAC and its production process. Now, the introduction to carbonation. Carbonation simply is a natural process that occurs when AAC minerals react with carbon dioxide and other moisture from the environment. This reaction is not just a simple interaction, it actually changes the material's properties. Moving on to its impact, the impact of carbonation on AAC is very significant. It actually accelerates the aging process of AAC that leads to structural and property degradation. Over the time, what has been noticed is that it can result in increased cracking, shrinkage, and overall reduction in materials durability and strength. For understanding what actually is the carbonation process, I will take you deep towards it. The carbonation process involves transformation of minerals within AAC into calcium carbonate and silica gels. These changes are influenced by environmental factors such as humidity, carbon dioxide levels, and the specific curing condition of AACs. And this transformation is at the heart of why and how AAC changes over time. Now, simply moving on to definition and measurement, like how it is defined or how carbonation can be measured in AAC. To monitor and manage carbonation, we first define it using a specific formula that actually calculates the degree of carbonation based on the carbon dioxide content present in the AAC. We measure this content through a method that is known as thermal analysis, which is performed at the temperature range of 600 degrees Celsius to 800 degrees Celsius. This method specifically targets the detection of that, what I have already said, like detection of the calcium carbonate, which is taken as a key indicator of carbonate. And talking about the research and application regarding the carbonation of ACs, through standardized measures and continuous research, we enhance our understanding of AAC's durability. This ongoing research not only improves the accuracy of our assessment, but also guide us in developing more about developing more concept about the use of AAC that can actually withstand the environmental challenges over long period of time. Now moving on to the other research, that is what has been noticed is that recycled AAC actually works as a replacement for the sand. Like in the pursuit of sustainability, one key innovation in AAC manufacturing is replacing traditional sand with industrial byproducts like of EPW, expanded perlite waste, and also iron tailings. These materials are not just waste; they actually enhance AAC's properties and contribute to environmental conservation. Now, how material is substituted? Okay, integrating up to 10% of these byproducts maintains AAC's structural integrity without compromising the compressive strength of the structure that we are building. However, increasing this ratio beyond 15%, what has been noticed is that it significantly reduces the strength. Now, talking about the thermal and mechanical impact of the substitution, this substitution actually lowers the thermal conductivity. That means it improves AAC's insulation properties. Some mixes also has been noticed that they get enhanced compressive strength and reduced weight. Now, talking about the environmental benefits of recycled AAC. Using recycled materials actually reduces the landfill waste and also cuts the carbon footprint of AC, which actually is the main motto of sustainability. Economically as well, it decreases the cost that is related to stand procurement and waste management. Now, talking about the practical application and limitation, though effective in flooring, the use of recycled AC in walls and other structural elements needs more testing, needs more vast testing, but it has actually shows promise for like non-load bearing structures. Now, talking about the future prospects, as we continue to refine this process, recycled AZ actually has the potential to significantly impact sustainable construction practices. And now I would like to hand this stage to Kusi first. Now she will be explaining utilization of solid waste in AAC production.
Thank you, Rohit. Now we shall become acquainted with the utilization of solid wastes in autoclaved aerated concrete. We shall go through its effects, automated process, characterization, and performance insights. It basically involves the creation of lightweight, high strength masonry material with exceptional insulation and fire resistance properties. It is environmental friendly, emitting 67% fewer carbon emissions compared to traditional clay bricks. Now, looking at the waste substitution, which we have in the utilization of solid wastes, various industrial and agricultural wastes such as marble slurry, fly ash, and rice husk ash are also used as replacements for sand and binders. This substitution enhances physiomechanical properties and durability while reducing environmental impact. Now, looking at its impact on the properties, the use of substitutes can improve bulk density, moisture absorption, and compressive strength. Adjustments to calcium silicon ratios influence the formation of tobamorite and overall mineralogy of autoclaved aerated concrete. Research also indicates that incorporating waste affects the porosity and microstructure of AAC, thereby influencing its thermal properties. Ongoing studies aim to optimize waste content for improved performance and sustainability. Coming to its development, we should know that current research and development efforts are focused on creating AAC using various waste materials to enhance cost efficiency and environmental sustainability. Also, as we can see from the diagram, several wastes such as mining wastes, industrial wastes, construction wastes, and municipal wastes are utilized in the production of AAC. These wastes can be substituted by several raw materials such as lime, siliceous materials, and gypsum, which then undergo autoclave curing to finally produce the autoclaved aerated concrete, which is lightweight and has high fire resistance. Now, Ishani shall present some vital experimental data that supports the benefits and applications of AAC.
Thanks, Kushi. Now, looking at some experimental data will give us some very valuable insight into the topic. The first chart, as can be seen, is displays the consumption of raw materials and energy for various building materials. It can be noticed that AAC stands out by requiring significantly less raw materials, measured in kilograms per cubic meter, and lower energy, measured in kilowatt hours per cubic meter, which makes AAC an appealing choice for sustainable construction. Moving towards the next graph, this shows us the stress strain graph. Here, as can be seen, it examines two types of concrete blocks, namely CB2 and CB6. Both samples show how stress increases with strain, and which is a key measure of material strength. Despite their similarities, subtle differences in their curves might indicate that the variations in material consumption or mechanical properties. And this is important for understanding how the material behaves under the load. As can be concluded from both the graphs, AAC exhibits lower environmental impact in production compared to traditional materials like clay, bricks, and calcium silicate unit, making it a sustainable choice. That was shown in graph 1. Also, from the stress strain analysis, uh, it provides insights into the durability and strength of concrete blocks essential for structural applications. Now, wrapping up with the experimental data, Rohit will further explain innovations and the further innovation and give us very valuable insights into the topic.
Yes, Shani. Now, as we advance into the future, AAC production is embarrassing groundbreaking technologies and innovation that actually enhances sustainability and efficiency. Now, talking about the advanced material blends, we are actually integrating nano materials and smart additives that improves AAC's thermal resistance and structural integrity, alongside developing hybrid kind of AAC that would be incorporating organic materials for better environmental outcomes. Now, even AAC is being used in 3D printing, like, yeah, actually 3D printing the entire structure. AAC is now being utilized in 3D printing for on-site production of like that could be complex structure, that could be simple structures that reduces waste and cutting transportation cost very significantly. Now, talking about the smart sensing of AAC, we are embedding sensor within AAC, like within AAC blocks that can actually monitor structural health in a real time or real world. That enables proactive maintenance and that also ensures safety through early detection of the potential issues that might help us from saving our structures. Talking about the improved recycling techniques, our new recycling methods transform AAC waste into high quality products, aiming for a zero waste production and utilizing AAC waste in various construction applications. Talking about the regulatory and standard development, we are also actively involved in setting international standard for AAC and developing guidelines that can promote AAC's use globally. Now, as we conclude our presentation, let's recap the significant advancement and the promising future of AAC in revolutionizing sustainable construction. So, AAC plays a pivotal role in reducing environmental impact through its superior insulation capabilities and its ability to significantly lower carbon emission. Its unique properties not only enhance building performance but also contribute to a greener planet. Talking about the future potential unlock, our exploration of AAC has shown how innovation through waste utilization can future enhance its properties by incorporating industrial and agricultural wastes. AAC production becomes even more eco-friendly, supporting sustainable building practices and reducing wastage. But it has a call for a global standard with the advance in technologies like 3D printing and nano enhancement. AAC's production in smart construction is rapidly expanding. To fully realize these benefits on a global scale, there is a crucial need for international standard that promote AAC and like adapt to the new changes and optimize its contribution to the construction industry throughout the world. In closing, AAC stands as a testament to how innovative building materials can create sustainable and efficient environments. It is our responsibility and opportunity as future leaders in the construction industry to advocate for and adopt such materials that pave the way for a sustainable future. As we reach the end of our presentation, we want to express our gratitude for your attention and engagement. We hope that our discussion has provided you all with a deeper understanding of AAC autoclaved aerated concrete and its role in shaping a more sustainable future in construction. We have also provided the references, the research paper, the scholar paper that we have used throughout our research in the presentation. Uh, Thank you once again for the opportunity to present our research and findings. We appreciate your time. And if you like to discuss any aspect of our presentation further, please feel free to reach out after this session. Thank you.